For this lesson, we're going to be taking a look at the way that data can be distributed, and we're going to be looking at a very specific distribution of data called the normal distribution. Now, it has a very specific shape when you graph it. And so I've actually got some examples here of a normal distribution in the middle and some non-normal distributions to either side of it, because I wanted to illustrate this idea. One of the things that distinguishes, this is not the only thing, one of the things that distinguishes a normal distribution is that the mean, median, and mode for the data, they will all occur at the same place. If the mean, median, and mode are not in the same place, you will typically have what is known as skewed data. Now, there are many other types of distributions other than what I'm showing you here. I don't want you to think that this is somehow all that are possible, but this is a very common arrangement. Either something that's completely symmetric, which is a normal distribution, or you have something that is skewed to the left or skewed in the negative direction, or you have something that could be skewed to the right. So first of all, you need to have this condition, which is the mean, median, and mode are all the same. And another thing is that characteristic bell shape or bell curve. You may have heard it referred to that way as well. So this is kind of that classic example of normally distributed data. Now, you won't normally have to determine whether or not the data is normal. Usually it'll be given to you and you'll be told this is normally distributed data, or you'll be told that you can assume that this is normally distributed data. Normal distributions are very common in natural processes. So a lot of experimental data in the real world would be normally distributed. There's a lot of stuff you can do in psychology that could be normally distributed. So doing surveys, whenever you're involving humans, either measurements, talking about heights or weights or shoe sizes, or when you're getting humans to respond to certain types of questions, you can actually get a surprising number of those all turn out to be normally distributed data, which means you can apply the mathematics of normal distributions to them. So let's move on a bit from there. In a previous lesson, I had talked about standard deviation, and standard deviation is a measure of how much your data moves away from the mean. So you can see here in the middle, there's the mean of the data. In this case, I'm using the letter mu, so that would be the mean of the population data. You might also be referring to this as X bar in your own work, because quite often we'll be doing sample data. And so the standard deviation is a calculation you can perform on any data, and it just gives you an idea or an indicator of how the data is spread around your central measurement, which in this case is our mean. But if it is normal data, the spread actually takes on a really well-defined form. And that well-defined form results in approximately 68% of your data will be within one standard deviation of the middle. So that means we could go +1 standard deviation to the right, or we could go -1 standard deviation to the left. And what's left over, all of the data points made up between that plus or minus 1 standard deviation, or another way to think of it, that part of the normal curve or the bell curve, that makes up 68% of the data. So that actually, sorry, I didn't mean to do that. I meant to do that. So that actually tells you that 34%, roughly, 34% of the data is in that part of the curve, and 34% of the data is in that part of the curve. And each one of these equally spaced intervals can be broken down that way. Now, this next interval doesn't hold 34%. Obviously, it holds much less than this part of the graph. But the theory about normal curves tells us that within 2 standard deviations, you have 95% of all of the data. And within 3 standard deviations, you get to 99.7% of all data. So that means once you work your way out to plus or minus 3 standard deviations, you shouldn't be seeing, only exceedingly rarely should you see any outliers, should you see any data that is beyond 3 standard deviations on either side. So that allows you to make predictions, that allows you to test certain theories with respect to the data. And all of this is contingent upon the idea of the data being normal. Now, sometimes in math, I don't want to go too deep into this, so I just wanted to mention it because sometimes when you talk about standard deviations, you will see, or sorry, not standard deviations, I'm sorry, I misspoke there. Sometimes when you talk about the normal distribution, you'll sometimes see this expression. And it's quite complicated looking. It's got some unusual parts to it. For example, it's got pi. And pi we normally think of as being related to circles and to angles and to trigonometry. So it really begs the question, what is that doing there? And I'm certainly not going to delve into that. I've seen a number of really good videos. You could look them up online of people delving into the mathematics of why this is here. Now, the reason for doing this, I talked about the area underneath this curve. I talked about this area and this area making up 68% of the area. Now, there are times in mathematics where it's actually convenient for us to have everything referring to 1, the number 1. And so what you can do, and that's what this expression accomplishes, what this expression accomplishes is it takes all of the possible area under that normal curve, even though that curve stretches out to infinity in theory on either side, you can, by making these changes to the expression, you can result in an area of 1. And that's just convenient. And again, I'm not going to get into depth about that. So if you see this, especially if you're doing research on your own, this is still a reference to the normal curve. It's just it's in a more complicated form. We won't need to use that. I'm just making you aware of it, so if you see it, you're not thrown off by it. Okay, so this is just basically capturing what I was chatting about there. So the normal curve has some very specific properties. There are some very specific calculations and types of analysis you can form when you're dealing with data that has a normal distribution. We are going to specifically talk about z-scores, which I have mentioned in the past, and we're also going to be talking about standard deviation because these two things are linked to each other. Z-scores and standard deviations are really just two sides of the same coin. And so we're also going to be talking about something that you may not have heard me mention before, which is something called a continuous random variable. The idea here is that when we have our mean in the middle and then our curve on either side of it, a continuous random variable just means that the variable can take on any values to either side of the mean. And the mean itself could be any value. And I realize I'm sometimes mentioning things here that I'm not going to be going into detail in this particular lesson. The probability of any single exact value is 0. We don't have to get into the subtlety of that. Some of you watching this may already be familiar with it, but I know that some of you won't be. So I'm going to move on from there without giving it any more attention. Okay, so I've got some experimental data here, and I pulled this data from a textbook or from an online source. The idea is you've got planes have been instructed to land at a specific location on a runway, and the planes are basically you're testing how precise the pilots can be in flying the plane to that spot on the runway. right? So how close can they touch down to that spot? And so this data tells you where they landed. Now, this is not with respect to a specific location, because if it was with respect to that location, some of these would be positive and some would be negative. So what this data is actually probably measuring is the distance x that they landed from the end of the runway. Now it wouldn't be that end of the runway. It would be the runway that they've already flown over. So let's say that what this experiment is measuring is how far past the end of the runway do they need in order to make their landing. And so we've got this data set. We've got a mean value of 14.63. We've got the standard deviation of the sample of data, because obviously this data is not a population data set. This is not all of the possible values of all the possible planes trying to make that landing. This just happened to be the number of planes that were used for this experiment. And so we see we have a standard deviation of about 3.26. So using that data, what does that tell us about this landing? And I think, so now moving on here. So I want to first tie in that data to just the general idea of the graph, because it's actually quite powerful. And without doing any sophisticated calculations here, I'm actually just going to use this idea of the different percentages here. And actually, I'm not even really going to be referring to the percentages yet, will I? Maybe a little bit. Yes, a little bit I will be. And the idea of being plus or minus some standard deviations. So the mean, 14.63, so that's going to be this middle part. So that's about 14.6. Now let's take a look at what the question actually wants us to figure out. What's the probability of landing at 18.3 meters or less? Well, 18.3 meters. Let's take a look at one standard deviation. If I take 14.63 and I add the standard deviation of 3.259, I end up with about 17.9. So 17.9 meters would be there. And so from this, I can actually come up with a pretty good estimate for what I think the answer to A is. So I'm going to say approximately. Now let's take a look. Well, first of all, if the middle is at 14.6, that means that 50% of the data would be above 14.6 and 50% would be below. Now we want to know what is the probability of landing at 18.3 meters or less. So I'm not interested in everything above 14.6. I'm really only interested in everything from 14.6 up to 18.3. But for the purpose of this discussion, 18.3 is close enough to 17.9 for me to at least make an estimate. And we already talked about how much space this part of the graph takes up. We said that's about 34%. And so putting those together, the total amount of graph that's below 17.9 is going to be 50% plus 34%. So I expect that this answer is going to be about 84% of the planes are expected to land at 18.3 or less. It should be actually a number a little bit bigger than this. What about for part B? What's the probability of landing past 18.3 meters? Well, that's going to be the remaining part of the graph. And if 50% is here, 34% is here, making 84%, that remaining part here must be about 16%. And I expect that to be a little less than 16%. For the same reason I expected this one to be a little more than 84%. What is the probability of being between 12.2 and 18.3? Okay, well, you can probably guess where this is going. 12.2, 14.63 minus 3.259, that gives me 11.3. So this number, I'll put it on another color, this minus 1 standard deviation, actually it's closer to 11.4. So I'm interested in now, things are getting a little cluttered here, so how about I just clear some stuff off. I'm not interested in all of this negative side. Now I'm only interested in, well, I'm interested in down to 12.2, so not quite all of this. So how much of my data is going to be between the purple mark and between, so essentially how much data is between 11.4 and 17.9? Well, that is about 68%. But we actually have to go a little bit to the right of 11.4, but we also have to go a little bit to the right of 17.9, which means this whole arrow is just going to shift to the right by a little bit. I still expect it's going to be less than 68%, because we're going to lose more than we gain there. But these three estimates should actually be quite reasonable. Now, why did I go through that exercise? Well, first of all, to show you the power of just understanding this graph and what it means. And secondly, that it's worthwhile, if you have the ability to do so, it's worthwhile to do an approximate set of calculations just to give you an idea of what kind of ballpark you should expect your answers to be in. So we're going to come back to these and double check them. And I am doing these honestly in the sense that I have not worked out our next answers well enough, or it's been long enough ago that I don't remember them off the top of my head. So this is a reasonably fair example on how to do kind of confirmation or predictions to confirm your answer. Okay, so the first thing we have to figure out is what's the probability of landing at 18.3 meters or less. Now, I've talked to you about where 18.3 meters would be on our graph, and so that's going to be at just a little bit past 1 standard deviation. I don't know if you can make this one out because I made it so small. There is the mean value, which means this first bar is the mean value plus 1 standard deviation. So 18.3 is going to be around there. And so this is where I'm going to introduce the next idea that goes along with this, which is we're going to make use of z-scores. Now, if you remember what I've talked about, or if you've learned it on your own, z-scores basically give a number associated with the number of standard deviations. So for example, this line is a z-score of exactly 1. The mean, the middle line, is a z-score of 0. The next line is a z-score of 1. The next line is a z-score of 2. Basically, the z-score tells you how many standard deviations are you away from the mean. So to do this question, part A, the first thing I'm going to do is figure out what is the z-score for 18.3. So I take that data value, 18.3, and I subtract the mean value, which is 14.63, and I divide that by the standard deviation. In this case, it's the standard deviation for the sample, and I get 3.259. And I do that calculation, I get 18.3 minus 14.63, and divide that by 3.259. And I end up with approximately 1.1261. 1261. So what this is telling us is that the value 18.3 is 1.1261 standard deviations to the right of the mean. It's positive, and that means it's to the right of the mean. Now, I mentioned to you early in the lesson, and it might have seemed a bit obscure at the time, I mentioned to you the idea of making it so that these curves have a total area of 1. And you know what? I should have mentioned this then, so I'm sorry I'm only mentioning it now. The value of having an area of 1 underneath these curves for our purposes is that a probability of 100% is represented as the number 1. And so what that means is that if you have normally distributed data, then you can look at this curve in terms of probability. And if you measure various locations on this curve, the area under this curve, it tells you the probability of, well, I'm going to, let me show you as we work through it. We're going to use this z-score to determine the probability of getting to 18.3 or less. So basically, I am trying to figure out what is the area under this entire curve up to the value 18.3. And we're going to use the z-scores to determine that. Now, in order to do that, we have to make use of what's known as a z-score table, which will be provided to you, or it's something you could look up online. I have a positive z-score, so I go look in the portion of the z-score that is positive, and just try to keep this in your head, 1.1261. So I've got some electronic versions of z-scores here. This is the negative z-score table. Here is the positive z-score table. And I am looking for 1.1261. So I come down here, and there is 1.2. Actually, I said 1.12, didn't I? Okay, so there is 1.1, and I want 1.12. And so now I look, actually from a rounding perspective, it's closest to 1.13. This z-score table only goes to 2 decimal places. So if you look at what I've circled here, that's 1.1. And then you add to that the other part that I got here, which is 0.03. I end up with 1.13. And that is approximately the same as the 1.126 that I was looking for. And so where do those two things converge? Right there at 0.8708. So a z-score of positive 1.13 gives me a probability of 0.8708. And z-score tables quite often will come with a little graphic to help remind you of this. So what that's saying is that there's an 87% chance, or 87% of the data is going to be at this score or below. So we can take that back to our note. And so now we can say the probability of being at less than or equal to 18.3 meters is equal to 0.8708. And we might as well say that's approximate, because even then we had to do some rounding. So the probability of landing at this point or earlier is about 87%. Compare that to our prediction. I said 84%. And for a ballpark prediction, that's still valid. What's the probability, moving on to the next one for part B, what's the probability that it's going to land past that point? So again, there's our 18.3. Now in this case, we don't actually have to do any additional we don't have to do any additional z-score calculations. We already have the numbers we need, because the probability of landing greater than 18.3 meters is just the same as 1 minus the probability of less than or equal to 18.3 meters, which is 1 minus 0.8708, which works out to be 0.1292. So about 13%. And finally, part C, between 12.2 meters. Oh, sorry, and let's go back and confirm that. So about 13% I said, and I had 16% for my prediction. And now for part C, we already know what the z-score for 18.3 was, And I don't need to write that as a z-score. I just need to say that the probability of less than or equal to 18.3 was 0.8708. Now we have to figure out what is the z-score that goes with 12.2. So I'll just use 12.2 as my subscript here. And so I do the value itself, the x value itself, 12.2, minus the mean, which is 14.63, divided by the standard deviation, 3.259. And from there, I get 12.2 minus 14, sorry, have to do that again, 12.2 minus 14.63 equals, divided by 3.259. And this one gives us a negative z-score of negative 0.7456. 7456. And as we discovered, so that's approximate, but as we discovered, our z-score table actually only goes to 2 decimal places. So we're going to write this as 0.75 because that's all we're going to be able to get from our z-score table. This is a negative value, so we're going to find 0.75 on this table. Here is negative 0.7, and so negative 0.75 would be there. I find where those two values cross each other, which is 0.2266. So that's saying that when this is the value of 12.2, 22.66% of the data is going to be less than that. And now we put those two pieces together. So 0.2266 for that one. Let's extend that page, give ourselves some more room. So the probability of being less than or equal to 12.2 is 0. I think it was 2266. 0.2266. And we already had 8708. So if we look at that in terms of our normal curve, then essentially what we have are two curves. So I'm just going to sketch them here, one above the other. That's not a good choice. There's the first one. There's the second one. The first one told us that there was 87%. So in there is 87.08% of the data. And the second one, which used, and this was for 18.3, and then the second one, which used 12.2, gave us a result of having 22.66%. And what we have to figure out now is, using these two numbers, how do I figure out the data in between? So how do I figure out the area represented by that purple section? And hopefully you can see that. What I need to do is take what I have in red here, and I have to get rid of this green part on the left. And that's going to give me the purple. So if I color code it, the probability that we are between 12.2 less than or equal to x less than or equal to 18.3 is equal to the probability of less than or equal to 18.3 minus, and I subtract from that, the probability of less than or equal to 12.2. So it just works out to be a simple subtraction, which is 0.8708 minus 0.2266. And our final answer, 0.8708 minus 0.2266 equals 64.42. and those are all approximate, 0.6442. So that means that there is a 64% chance of landing between, this is why I don't often do concluding statements using this tablet, because it does slow down things quite a bit, between 12.2 meters and 18.3 meters. And how did that line up with my estimate? So I got an answer of 64%, and again, my estimate was 68%. So as far as having something to look back on and feel pretty good about my final answer, I'm pretty happy with that. And I believe that's it for these exercises. So for my notes, for my classes, I'll be including a copy of this Z-score table. You can find them online though. Learn how to use the paper copy. You can also find online tools that will just let you enter a value and it will tell you the Z-score as well. And there's some assigned work from our currently in use textbook.